electric field at a point outside the spherical charged sphere. Now, on the surface of the sphere. When I say this, what I mean is, if the point P is brought and placed on the surface of the sphere, on the surface of the sphere, small r becomes equal to capital R. Therefore, E becomes equal to Q by 4 pi epsilon naught capital R square. No harm in that. Okay. Now the next question is, if the point P is brought inside, what will happen? Let us try to understand that. I will rub this off. This is the field at a point outside. This is the field at a point on the sphere. We have to find out electric field at a point inside a uniformly charged sphere. Okay? At a point inside the uniformly charged sphere. Imagine this is the sphere whose radius is R. Okay? Charge Q is there. Electric field is pointing upwards like this. Now, you are placing a point P somewhere here. Therefore, what do I do is, I construct a Gaussian surface such that it passes through that point. This is R sir. This is the Gaussian surface I draw. The point P is here. Okay. Let me, instead of dotted line, because I am using yellow chalk piece, I will put it bold. This is the Gaussian surface I have drawn. This is the Gaussian surface. Okay. I will write Gaussian surface. The point P is here, therefore you take a surface here. ds. You draw unit vector, it will be normal to it. This is area ds. Okay. This is at a distance r from the point charge. Okay. From here to here, the distance is r. Now, in order to determine electric field intensity due to this point charge, due to this uniformly charged sphere at a point inside, you have to find out what is the total flux. First step is you have to find out what is the flux to the small surface. Flux to the small surface, we all know, flux through surface ds d phi E vector dot n unit vector ds. No harm in writing that. Is that okay to you? Now total flux phi is equal to integral of the surface E vector dot n cap unit vector ds. Since E and ds are parallel, E and n are parallel, theta 0, cos 0 is 1. This will become E vector dot n unit vector ds will reduce to EDS. No doubt. Now, from Gauss's law, I write phi E, okay, is equal to Q dash by epsilon. Very important here. The charge Q is distributed uniformly throughout the sphere of radius capital R. Point P is here, and the electric field at this point P will not be due to the entire charge enclosed in the sphere of radius R, but will be due to the sphere of radius smaller. The charge within this sphere of radius smaller can't be Q, it has to be less than Q, and therefore I written this Q dash. The problem now is we need to find out what is the value of Q dash. For that again, surface charge density, volume charge density, I write it as charge upon volume. Therefore I write the charge Q dash is volume 4 by 3 pi r cube rho. Is that okay to you, sir? Charge is volume into volume charge density. So let me substitute this here. This will become phi E is equal to 1 by epsilon naught 4 by 3 pi r cube. This is equation 2 for me. This is equation 1 for me. Is that okay to you? Now equation 1 I will write it here. Integral of the surface E vector dot n unit vector is equivalent to, because theta is 0, this will reduce to ADS. Okay? Into is equal to, this is equating 1 and 2. I will write like this. From equations 1 and 2, I write E integral of the surface ds is equal to 1 by epsilon naught 4 by 3 pi r cube rho. This is E, surface area of the sphere of radius smaller 4 pi r squared is equal to 1 by epsilon naught 4 by 3 pi r cube rho. Now strike off 4 pi r squared, you are ending up with E is equal to R rho by 3 epsilon naught. R rho by 3 epsilon naught. Electric field intensity at a point inside a uniformly charged sphere is R rho upon 3 epsilon naught. Then at the center, at the center, E will be equal to 0. At the surface of a solid sphere, E will be equal to R rho by 3 epsilon naught. Now, having derived expressions, one for electric field at the center is 0, electric field at the surface is R rho by 3 epsilon naught, electric field at any point inside smaller rho by 3 epsilon naught, we can plot a graph to show the variation of electric field from the center of the charged spherical sphere. Let me draw a graph to show you. The graph will look like this. Okay? If you draw a graph, taking distance along the x-axis, electric field along the y-axis, at the center electric field is 0, it reaches a maximum at the surface outside the surface at a point outside is q by 4 pi epsilon naught r squared. It is inversely proportional to r squared, therefore will decrease go like this. Okay, you say this is at the surface, it is maximum. Outside it decreases. Outside it decreases. Outside it decreases because E is inversely proportional to r squared. Here this must be equal to smaller, must be equal to capital R. This is maximum. Okay, or it is R, in fact R. Here it is maximum, this is E max. At the center 0. This is how the graph will look like. Is that okay, team, sir? So this is the first application we have seen for electric field intensity due to a uniformly charged sphere at a point. First we have seen outside, then we have seen on the surface, then we have seen at a point inside the charged spherical conductor. We will try to see one more application, and then if time permits we proceed, otherwise we will wind up. Field due to a solid cylinder. Let us consider this to be a solid cylinder of radius r, charge uniformly distributed throughout the volume of the cylinder. Let length of the cylinder be let rho be its volume charge density. I repeat, these parallel lines with this dotted line, the dotted line is the axis of the cylinder. I have drawn a cylinder, caps are not shown here. This is a cylinder of radius r, and VR, its length is L, volume charge density is rho. We are given some point in between inside the cylinder where we want to find out electric field intensity. Therefore, I construct a Gaussian surface such that it passes through that point. Okay? This is R. The radius of this imaginary cylinder drawn inside this is smaller, and this is my Gaussian surface. This is my Gaussian surface. Now we are interested field at a point inside. This is what we are going to see. In order to determine electric field at a point inside this solid cylinder, I have drawn a Gaussian surface, imaginary surface of radius r such that this cylinder of radius r and the cylinder of radius capital R are coaxial with one another. Let me take a small surface of area ds. Therefore, I write flux through a small surface of area ds. I write this as E vector dot n unit vector ds. You take positive charge, electric field will be pointing outwards, unit vector must be drawn normal to the surface, E and N are parallel to each other, therefore it will be E ds. Therefore, total flux phi E is equal to integral of the surface E vector dot n unit vector ds. This is equal to E into integral over the ds. This will be equal to E surface area 2 pi r circumference into L. I will call this as equation number 1. Is that okay to you? I have taken the surface area of the cylinder. Now this caps I have not taken. Why? If you take caps, you take a small surface, area vector or unit vector will be normal, electric field will be pointing outwards, therefore E and N are perpendicular to each other, theta will be 90, cos 90 will be 0, therefore I say caps of the cylinder do not contribute to flux. Do not contribute to flux because E is perpendicular to ds or n unit vector. Okay, this will be 0. Theta will be 90 degrees perpendicular. Theta is equal to 90 degrees. Cos 90 will be 0. Therefore, from process law, I write phi E is equal to Q by epsilon naught. Now we have taken rho, volume charge density. Therefore, we have to take the radius, volume is here. Volume is pi r squared L into rho upon epsilon naught. I will call this as equation 2. 1 and 2 are one and the same, equating 1 and 2. We get E 2 pi RL is equal to pi r squared L rho by epsilon naught. Pi will go off, R will go off, L will go off to give me E is equal to R rho by 2 epsilon naught. This is electric field due to a solid cylinder at a point inside the solid cylinder. Similarly, we have to find out what is the electric field at a point outside. Hope you follow this. Okay? If this is clear to you, I will go ahead to discuss how to determine electric field intensity due to a solid cylinder at a point outside. Let me rub this off. Let us say this is quantity is given outside, and therefore I am drawing a Gaussian surface such that it passes through that point where I want to find out electric field intensity, and let the radius of this Gaussian surface be smaller, and let the length of the cylinder be L. Is that okay to you, sir? Is that okay to you, sir? We proceed exactly the same way. Exactly the same way. Okay. Now, flux through elementary surface ds. Okay. E vector dot n unit vector into ds, flux through curved surface of the cylinder. When I say curved surface of the cylinder, I am taking this portion alone, not the caps, only the circular portion. Okay? Then curved surface of the cylinder, phi e is equal to integral the surface E vector dot n unit vector ds, integrating that 2 pi small r L. This will into E. This will be equation number 1. As I said before, caps, whether you take the upper cap or the lower cap, this will not contribute to electric flux. As I said, if you take a small surface, the unit vector and electric field vector will be normal to each other. They will not contribute to electric flux. Therefore, caps of the cylinder do not contribute to electric flux. From Gauss's theorem, I write phi e is equal to q by epsilon naught. I have to substitute for q. Phi e volume pi r squared L into rho upon epsilon naught. This is equation 2 for me. Is that okay to you? From 1 and 2, E 2 pi r L is equal to pi r squared L rho by epsilon naught. Pi L goes off. So we end up with E is equal to r squared rho by 2 epsilon naught. That will be the electric field intensity at a point inside the charged spherical conductor. So at a point outside. I'm sorry. At a point outside the charged spherical cylinder, at a point outside the charged spherical cylinder, the electric field is given as E is equal to r squared rho by 2 epsilon naught r, where r is the radius of the solid cylinder, rho is the volume charge density, r is the distance at a point outside from the charged cylinder, epsilon naught is permittivity of free space. Exactly in a similar way, we need to see what is the electric field due to a hollow cylinder and Poisson's and Laplace's equations. Probably in the next class we will continue. We stop here until we meet next. Goodbye.